in this problem, I have this blue wire, which is perfectly conducting set of wires, and they can make up a set of rails on which I place this bar. So this bar has a length L, sort of, I'll put here, inside the set of rails, length L. It has a resistance R, and it is inside a magnetic field. So we'll say this magnetic field goes into the page, so we have some magnetic field B. So the blue rails have no resistance, and we're also going to say that there's no friction, and we're going to send the bar off to the right at some initial speed v0. So we'll put that initial speed v0. And we're going to ask the question, so how far does this bar go? How far before it comes to rest? Okay, so how do we think about this problem? It starts at, say, some length x from the edge of these set of rail loops. We can gives ourselves a coordinate system. We call that positive x and that positive y. And let's take for a minute to try to visualize what's going to happen. Okay, so as this bar moves off here to the right, there exists a loop in this magnetic field. I'll trace this loop here. It's a conducting loop, and this loop contains a magnetic flux due to this magnetic field into the board. So as the bar moves off to the right, that amount of magnetic flux enclosed in that loop increases. So we know we have this increase in magnetic flux. So we know from Faraday's law that this changing magnetic flux is going to lead to an EMF around this conducting loop. And that EMF then is going to lead to a current in that conducting loop through this bar that has a resistance of R. Okay, so we also know that a wire conductor that has a current in it, a current-carrying wire in a magnetic field, feels a force on that wire. So presumably, since there's no friction, no drag, or anything else to slow this down, if this thing is eventually going to come to rest, it's this force which is bringing it to rest. So that gives us sort of a strategy to go on. We're going to find the flux to the EMF to the current to the force, and then use that to see how far the bar travels before it comes to rest. All right, first with magnetic flux. So the magnetic flux is this integral B dot over this area element, and so here we'll say the magnetic field is into the page, the vector perpendicular to the area is into the page, so this just becomes B times the area of the loop. Okay, so the area of the loop, then, we're going to say this is square. It has a length x and a height L. So that's our flux. We want the changing flux to calculate the EMF. So the derivative of the flux with respect to time, well, B and L aren't changing, but x is as the system moves to the right, as the bar moves to the right. So we have dx dt. And dx dt then is just the velocity of the bar. So it's not the initial velocity, it's the velocity at every point in time in the future is going to lead to the changing flux. Okay, so we've got the flux. Now we want to calculate the EMF. So the EMF is equal to the negative derivative of the flux, which is then equal to negative B LV. All right? And so if that's the EMF, now we can find the current. The current then is the EMF over the resistance. Now, we said that the resistance through all the rails is 0, so the only relevant resistance is the resistance in the bar, which is R. So the current then is BLV over R. Current is just a positive number. All right, so we have a current, and now we want to know what is the force then on that current. Okay, so the force, if we give ourselves some space here, look at this here. So the force on a current carrying wire is equal to the current times this L vector cross the magnetic field. This is the length of the wire, and the direction of this L vector is the direction of the current. Okay, so that brings us back to, so what is the direction of the current? And so if we want to use Lenz's law on this system, as the velocity moves to the right, there's an increased magnetic flux into the page. And so there's going to be a current induced in that loop to try to oppose that increase in magnetic flux. So it is going to want to try to, well, this is the induced magnetic field. It's going to try to come out of the page to be able to change the increase in magnetic flux into the page. And so using the right-hand rule around this loop, we find that the current has to be going counterclockwise, to create a magnetic field to oppose the increase in magnetic flux. So that means the current is going up through the relevant conducting bar. Okay, so that gives us the direction of L. All right. So now to calculate this force, we have I, we call this L hat, well, L times L hat cross B, and L hat then is equal to positive J, and so we'll up. We can just use the right-hand rule. If we have our first vector up and our second vector, which is B, into the page, then the resulting force is in the negative x direction. So we have the so our force then is, and it's perpendicular, so we just get the magnitudes ILB and then negative I hat, negative x direction. So our force is equal to negative ILB I hat. Well, we found I from before. I was here, so we can substitute that into I, and we get a final expression for the force in terms of what we were given initially, equal to negative L squared B squared over R times V I hat. Okay, so here we have a force, and it's in the negative x direction. That makes sense because this force is going to slow the system down. And now we want to use this force to tell us how long it goes before it stops. Okay, so to do this is, go back to Newton's laws. This is the only force in the problem. So the sum of all the forces is equal to the mass times the acceleration. So we have this force is equal to mass times the acceleration. Okay, before I continue on, let me define a new parameter here. I'm going to take, just for convenience, I'm going to take this set of constants and just relabel it B, so I don't have to keep rewriting them over and over again. So now my F equals ma is equal to negative BV I hat is equal to M A I hat. Since everything's in the x direction, I'm just looking at the components, and so I have negative BV is equal to ma. So first of all, let me say this sort of substitution where I substituted all these for another constant, that's the sort of thing I do all the time, just so I don't have to, if I think I have a long calculation, I don't have to keep rewriting those variables over and over again. Though in this case, my choice of b is not a coincidence, because this expression, if you studied drag in Physics 1, is simply the expression for a system undergoing a linear drag force, and this is sort of the traditional constant used in that. So at this point, the derivation is identical to that system. But let's go ahead and do that anyway. And we're going to first just do this in a straightforward way, where we're going to integrate the equations of motion to try to come up with the trajectory, and see how, once we have the trajectory, how long the thing goes before it stops. All right. So let's start by integrating this thing. So negative bv, that's not a b, bv is equal to m, and a is the derivative of v. And so I want to separate the variables v and t in this system. So I'm going to take the t's on one side. Let's see, get the t's on one side, and I'm going to put those with the constants, negative b and m. And then on the other side, I'm going to gather all the v's. See, so this is the key point to sort of integrate in this way. I'm going to integrate these equations. I get the t's times on one side, all of the times on one side, all of the v's on the other side, and then I can go ahead and integrate both sides. So now I need the limits of integration. So I'm going to say the time starts at t is equal to 0, and it ends at some later time t, which at the moment I don't know. The velocity, well, it starts at some initial velocity v0 and ends at some final velocity we'll call v. And eventually we want to see where that goes to 0. Okay, so this, if we do the indefinite integrals of this is minus b over m t evaluated at 0 and t, and then this is equal to the natural log of v evaluated between v0 and v. Okay, so the first part then just becomes negative b over mt, and then this second part is natural log of v minus natural log of v0, the initial velocity, and by the properties of logarithms, this is the natural log of v over v0. So I want to solve for v. I want to find what this v is, and so to do that I take e to both sides, and so I get I go over here, e to the negative b over m times t, then is equal to e to the natural log of something is just that something, v0 over v. So we now have an expression for my velocity, which is our initial velocity, e to the negative b over m times t. So now we have velocity as a function of time, and we want to know how far it goes before it stops, so we want to find where the velocity is equal to 0. Interestingly, the velocity never goes to 0 in this expression. It exponentially decays, but it continues going on forever. So a way to say that is that so the velocity equals 0 at t goes to infinity. Fortunately, however, despite the fact that the velocity never goes to 0, it continues on forever, it only goes a finite distance. And so we can calculate that by simply integrating the equations of motion again to find the trajectory x of t. Okay, so looking at this expression again, our velocity is the time derivative of position, v0 e to the negative b over mt. So we bring the t on the other side, and now we've separated our variables again. We have all the x's on one side and the t's on the other, and so we can go ahead and integrate. Let me get a different color for that. So now, so this becomes the integral of dx, and then integral v naught e to the minus b over mt dt. Okay, we need limits of integration. Our dx from some initial position to some final position. And our time goes from our initial time, which is 0, to our final time, which is infinity. Remember, that's where v goes to 0 is t infinitely far away. Okay, so this sort of thing, it can be done, in fact, really done quite easily. We know that, we can look up in a mathematical table of definite integrals, we know that the integral of an exponentially decaying function, e to the a to the minus t dt, is just equal to 1 over a, where a is some constant. So we can use this expression to do this integral quite straightforwardly. And so this part just becomes x minus x naught, or delta x, and then this becomes v naught times, well, what's this expression here? In this expression, this a is the constant in front of the t, and so that constant is this b over m. So this definite integral then reduces to 1 over b over m, or m over b. So this delta x, that's the distance that it goes. That's what we're looking for. And it's equal to this expression here, which we know, so we can just go back and look up what b was. V naught m. B, as we defined it, was L squared B squared over R. So we get R over L squared times B squared. And that is then the distance that it goes. And you've seen this sort of thing in calculus. It seems qualitatively odd to say that even though it goes on forever, the velocity goes on forever, it goes a finite distance, but that sort of thing can happen if the function that you have is exponentially decaying. That's just saying, even though my function may extend forever, the area under that function is finite, and that can be shown to be true. But just so now we have this expression, and the question is, does this make sense? So first, it says that if v naught is larger, it goes a further distance. Okay, that makes sense. What about the increased mass? If mass increases, okay, well that means the acceleration goes down for the same amount of force, and if the acceleration goes down, then the distance traveled is going to increase. Okay, so that makes sense. What about the resistance increasing? If the resistance increases, then the current drawn is less. If the resistance increases, so I goes down. If I goes down, the force goes down, and if the force goes down, the acceleration goes down, and acceleration goes down, then the distance before it stops gets larger, so that makes sense too. L squared. Okay, if L squared goes up, well, for the same, assuming the mass and the resistance is the same, if L squared goes up, then you're going to have a larger force, because the force is here, right here. So for the same mass and the same resistance, if L goes up, the force goes up, and the distance traveled goes down, and so that makes sense. And of course, if the b goes up, then the force goes up, and your distance traveled goes down. So okay, so sort of doing our check, does this sort of make sense to how we expect things to happen? And it does. So that's an important thing to do. All right. And so if that's the answer, and that's one way to go about doing it, and that's all fine, I'm going to take just a couple minutes to look at this in a different way. There's, in fact, a shorter way to go about doing the kinematics of this problem that's worth pointing out what to see. So originally we had this expression, which is this negative BV is equal to MA. And we wanted to know what is the total distance traveled. And in doing this, we integrated this expression with respect to time twice. Okay, so looking at this a different way. So this is mass. The acceleration is the derivative of velocity with respect to time. Now, using the chain rule, because the velocity is also a function of x, is going to vary as x varies, we can write this as the derivative of the velocity with respect to x times the derivative of x with respect to time. Okay, and this latter part is just the velocity. So this is equal to mass times the velocity with respect to x. Okay, so now, if we look at what we have negative BV is equal to mv dv dx. These v's cancel, and we can do separation of variables with respect to x and v. So we have negative b over m dx is equal to dv. Now, if we go ahead and integrate these, what are our initial and final parameters? This is from some x initial to x final. This is from some v initial to 0. And so if I integrate that, I just get negative b over m delta x. And this is equal to 0 minus v naught. And this is now the distance traveled, which is what I want. And so delta x is equal to mv naught over b, which is exactly what we had before. And so this is another solution that was, in fact, much faster to be able to do. But you had to be able to recognize this transformation using the chain rule in this way for Newton's laws. And so you can ask yourself, how would I have ever known how to do that? And that's a good question, and practice, certainly. But the key thing to keep in your mind here is that in the original problem, we never cared about time. We were not given time, nor were we asked to find time. It was only in terms of velocity and position. And yet our first solution, where we used kinematics, we ended up integrating through time twice. And so this sort of transformation that I did here is a way to look at Newton's laws in terms of relating the position and velocity without ever having to know time. So in problems where that's the case, there's a chance that going through this method might be quicker.